Next talk is part 4 of Bjorn Poonen's tutorial, and it's a second talk on the Hilbert problem for the single integer.
Okay, thank you. So let me recall what the plan was. So last time I outlined a 4-step proof that Hilbert's tenth problem for any ring, for the ring of integers in any number field is undecidable. And so I explained some of those parts, and today I'm going to explain the third step part, which involves this condition.
Oh, that the rank should be the same.
Oh, sorry, that's here. Okay, thank you. Yeah. So right, the condition is that, so it's a condition on a pair of number fields, and one indicates the other. And the condition is that there should be some abelian variety defined over the smaller field that has positive rank over that field and keeps the same rank over that. Yeah. And so today I want to explain why having such an abelian variety, how you can use such an abelian variety to prove that OK is Diophantine in OL. Should I do something else?
Could you just remind me who was it that proved number 3?
Oh yeah, so this was well, it's a long story. So in 2002 I proved a weak version where for an elliptic curve where it was rank 1. And then Diophantine and I both realized that essentially the same proof I didn't really use rank 1. so it's actually, and then it was generalized to abelian varieties in the paper last year by Mieser, Rubin, and Diophantine. Actually, there's also a paper by Cornelis and Fedas and Zahidi around the time when I first did that first result. They also independently got a similar result. Yeah. So okay. So and then the proof I'm going to give is none of those. It's a new proof that hasn't been made publicly available yet. So you're all special. So all right. Okay. Hopefully it works. So, yeah. All right. I mean, I've shared it with a few people, but not. Yeah, it's not. I'll probably post it on my website soon. But anyway, so to just explain why, okay, so let me just do an example of how, well, of one way you can try to show that a ring of integers is going to be Diophantine in a larger ring. How do you impose conditions that force an algebraic integer to lie in a smaller field? So here's just an example of something that's a true statement. So if you have, let me just do, suppose you have an element of z adjoint I, and you want to impose some kind of conditions to force it to be actually just an integer, ordinary integer. So here's one way you could do it. You could suppose that, well, suppose that you have that alpha is not too big, the absolute value, the complex absolute value of alpha is less than 5, and also it's congruent. Even though you don't know yet that it's an integer, it's at least congruent to an integer modulo a fairly large ideal. So let's say, just for the sake of this example, suppose it's congruent mod 10. And when I say mod 10, I mean mod 10 times the ring it lives in. So okay, and so it's congruent to some integer. So for some integer. So and then if that's true, then I claim that these conditions force alpha to be an integer. And before anybody says raise the board, I will raise the board. Okay. And now I will lower the board. Okay. All right. So yeah. So I think if I draw a picture, this thing will become obvious. Or maybe it's already obvious to you. So where are in the complex plane? Where are the elements of z adjoint I that are congruent mod 10 to an integer? Well, I mean, first of all, I guess you have integers. Integers are congruent to integers. So we have all these. Okay. But if congruent mod 10 means congruent mod this, you could also have 10i. which is up here somewhere. And then you could have that plus 1, because this is congruent. This one's congruent to 1, this one's congruent to 2, and so on. So you have these going this way, and you have another row down here, minus 10i. So. Okay, so the congruence is enough. The congruence by itself is not enough to tell you that your element is in Z. But if you also know that it lies, that its absolute value is small enough, it's lying in this circle of radius 5. 1, 2, 3, 4. Actually, don't remember that. 19, yeah, okay. Yeah, what? So if you also know that your number is somewhere in this disk, and it satisfies that congruence, well, you can see where it has to be. Now it has to be an integer. So that's sort of the idea, except we have to, I mean, this won't work. I mean, well, first of all, we're going to have to generalize this to, we're going to replace, the idea is this is going to be the os of L. And we're trying to force elements of os of L to be inside os of K. So this is going to be the os of K. And then we need to find a way to generalize this. But also we want the conditions we write down to be Diophantine. And so, yeah, so it'll be a little bit more complicated than this. So here's the lemma of which this is sort of an example. Okay, so we're going to fix this field, the extension of number fields. And so the claim is, and this. Yeah, by the way, maybe I should say the proof I'm about to give, although it's a new proof, it basically uses similar ideas to what all the other people in the past were using. It just organized and, well, I guess it simplified in various ways. So I claim that there exists an n such that for all elements of OL, so this is the element that we're trying to force to be in OK, and all non-zero ideals, so I inside OK. So this is going to be the analog of 10 times Z. Yeah, so and all K in the smaller field. If you know that the element is small enough, and small compared to I, so that it was important there that 5 was less than 10.
Could I not be in OL if it's similar to 10 times Zi?
Well, I also want this number. I want to be generated by an ideal. I mean, here I implicitly used. I mean, this would not have worked if I had taken an ideal like that was generated by 3 plus I. Even though 3 plus I has the same absolute norm as 10, it would not have worked if I just knew, if I had a number that was congruent to 3 plus I, it could still be,
Yes.
it could be, sorry, that was norm 100, but anyway, you need to, or maybe it actually is okay in that case, okay, whatever, but yeah, so it's, yeah, I need to be, I think that's right. So it's important that it be an ideal and okay. And so, so let me write like this. So now I'm not able to talk about the absolute values directly. So instead of doing that, I'm gonna pose this kind of condition to say that alpha is smaller than I. And so you might ask, why don't I just say that alpha divides I? That also makes alpha smaller than I in some sense. But that alpha dividing I would make the norm of alpha less than or equal to the norm of I. But that would not be enough for what I want to do, because that would still allow me to multiply alpha by units. And by multiplying alpha by a unit, it could make it sort of very big in the sense of its absolute values. And so, but if you put enough of these factors there, then it turns out that this will actually force alpha to be small in all absolute values compared to the norm of I. Okay, so anyway, so that's And so the condition, so that the claim is if you impose this condition and you also have that it's congruent to something in the smaller ring of integers, modulo I. And when I write this, I really mean that I divides. So okay, you can maybe want to write this as I times OL. It's I is an OK ideal, and then I want to extend it to L. And also the problem is this K is not actually an algebraic. Oh, actually it was there. Okay, but oh sorry, but alpha is sorry, I meant to write K here. I need to do this for things that are not even integral. And so yeah, so this difference is, so this, when I write this, what I really mean is that if I take alpha minus K, then I divides the numerator of that. And so this is an element of the field L, and I take its numerator ideal, which is an ideal of OL. And then this, okay, if you want, I can write I times OL, like the extension of that ideal, in the invisible color. So, and then that's what I mean when I write a congruence like that. But then, the conclusion is if you have these conditions, just as these conditions here force alpha to be an integer, these conditions, just being congruent to something in K, will force it to be in K, in OK. All right. So this is how we're going to get a handle. Well, I mean, we'll still have to figure out how to impose conditions like these, but yeah.
What is a numerator ideal?
So if you haven't, so this is, I mentioned this very briefly last time. If you take an element of a number field, you can try to write it as a ratio of two algebraic integers, and you could try to write it in lowest terms, but that might not be possible because the GCDs don't exist in something that's not a PID. But you can still take the GCD in the sense of ideals. And so you can write the ideal generated by this element as a ratio of two coprime ideals. And then the numerator is just the ideal that's on the top. So that's the numerator ideal. Okay, any other questions? All right, so let me just sketch the proof of this one. So I mean, this is just some statement of algebraic number theory.
Sorry, does the numerator ideal live in OL?
Yes.
Okay, good.
That's why I put this invisible OL here.
Yes.
So both sides here are ideals of OL.
Got it. Thank you.
Okay, good. So the first thing I can do is, without loss of generality, I can enlarge L. I mean, if you enlarge L, then you just have more possibilities for alpha, and so you just have more stuff to prove. So it just makes it so it's making it no easier to prove it. So so there's no harm in enlarging L, and by doing that I can assume that L is even gal over Q if I want. And yeah. And also, so if I take a sigma that's in the if I take a sigma that's in the Gauss group of L over K, and if I'm given that alpha satisfies a congruence like this, then I can sort of eliminate K by applying sigma to this congruence and subtracting. And so if you apply sigma to this, then you'll get this is congruent to this smug. And here's where I'm also using the I as defined over K. So I'll get this, and then by subtracting, I'll get that sigma alpha minus alpha is congruent to 0 mod I. In other words, that I divides that ideal. On the other hand, I know that if I take this product, alpha minus 1 to alpha minus n, I also assume that divides I, which now divides sigma alpha minus alpha. Yeah, so. And now this is a little bit weird because you have all these alpha terms, and then these divide a single difference here. So you can imagine that just by looking at the sizes of things, we're going to get a contradiction. I mean, there's some work to do, but what you do is you take the norm of both sides now. The norm, say, from L down to Q of this, and now you know that that's going to be less than or equal to the norm norm L down Q of this other thing. And yeah, and now you just study what the, you just expand the norm as a product of conjugates. You just look at the absolute value. You take the absolute values of both sides, and you just get a contradiction from this. Unless, unless the only way you don't get a contradiction is if this is 0. Oh yeah, so I guess I should have said that it's either this holds or the norm is 0, or which means that alpha minus alpha. And that's what I want to have happen. Yeah, because that'll say that alpha is okay. So if you have this inequality of norms, you eventually, if I had room here, I'd put a couple more dots to represent the rest of the proof. There was a little bit. Okay, so that's the end of that proof. Okay, yeah.
I don't get what's the significance of including the n, because the hypothesis implies the hypothesis with n equals 1.
But if I just had it with n equals 1, then that would be a weaker condition here, and that would not be enough to force that alpha is okay. So it makes it the bigger n is, the stronger the hypothesis here is. So the claim this is part of the hypothesis. I'm saying that these two things imply this. Yeah.
But
Okay. So I'm just saying it's not enough just to have alpha minus 1 dividing I. That won't be enough to imply this. But if I have all these, if I have a much bigger product dividing I, that'll tell me more about alpha, and will be enough to get to alpha.
the hypothesis is there exists n bigger than or equal to 1. So n equals 1 is also okay.
No, n equal 1 won't work.
So where are we actually using like the n equals, like where does the step show that n
It
equals 1?
comes down into these dot dots.
Okay, so it's using the fact that n needs to be sufficiently large?
Yeah, I need it to be sufficiently large in order to get a contradiction from this inequality.
So is the n here has some connection with the degree of the...
Yeah, it's like bigger, it's bigger than some function of the degree and stuff like that, yeah. That's right. Yeah, I mean, okay, I can share, maybe I'll try to share this document with people, and you can see, if you really want to see what's going on in those dots. Yeah. Okay, are there more questions? All right, so now that I've looked at this, you can all see the dot. So, okay, so, all right, so here's another concept I'm going to use in this proof. So for a subset of a number field, I'll say that it weakly approximates all the integers. So this, by definition, my definition is that this means that, well, weak approximation usually is referring to taking a closure inside the product of all of the completions. And so that is exactly what I mean here. That Z should be in the closure of S in the product of all the completions. And so this is a product ranging over all the prime ideals of OK. And and so this case of P is the notation for the completion of K with respect to the p-adic absolute value. So it's like, so if K or Q, that would be, if K or Q, this would be like the product of all the Q sub P, the p-adic integers over all the prime numbers. And I'm not, there are no Archimedean places here, it's just the actual prime ideal. And okay, so this is, so that's the definition. And here, each of these fields has the p-adic topology, and then the product has the product topology. And so, but because of the way the product topology works, that's the same as saying that's contained in the closure of these if you take in for all finite subproducts here. Yeah.
Are you imposing finite support in the valuations in the product?
Say that again?
Like with the ATL, are you imposing like finite support on the product of the?
No, this is just the direct product of all of those topologies. So yeah.
Okay.
So this is just some big topological space. Yeah. Okay. So this is the same as saying, that you can that every integer is a limit of things in here. But it's to say that every integer is a limit in here. It's enough to say that for a finite set of primes that it's in the limit of things in the finite product. So it means that for every integer and for every finite list of primes, maybe I should let's use an M here. There exists a sequence that converges to K. So there's a sequence in my set in S, the set S that I'm testing, that converges to K. And converging to K, and to be converging in the product topology, it should converge to K inside this completion piece of I simultaneously for all. So it should be a single sequence that converges simultaneously for all I. For I equal 1 to n. Yeah. Okay, so yeah, so this is just topology, just getting this piece to be equivalent. And let me just write it in a couple of other ways too. So one more way. You could also say, just to spell out what it means to converge p-adically, that really amounts to some kind of congruence. So this is the same as saying that every integer can be approximated at least modulo some ideal, any ideal. So this is the same as saying that you can approximate it sort of that you can find something in S that's congruent to this number k modulo like pi to some power, and for these finally many i's, which is the same as taking the product of those prime power and letting I be that product of prime power. So having this thing is the same as saying that for any non-zero ideal, you can solve a congruence like this. So the congruence x congruent to k mod I has a solution. Has a solution in S. Yeah, because that's what it means to approximate K. Okay, so all right, so that's some notion. All right, so now I think so maybe I'll prove one more thing about this. So we'll use this later. So if you do have this condition that S weakly approximates all the integers, then one thing you can say, okay, and let's say and you have an element theta in OK, and let's say it's not 0. So then there exists an S in this set whose numerator is divisible by beta. Okay, and the proof of this is one line. So you just say, well, according to this last version of the definition, I'm going to look at the congruence. It says that x is congruent to 0 mod beta. This has a solution. Has a solution S and S, and you just take that S. and then this congruence, by definition, this congruence means that beta divides the numerator of the difference. That's what I mean when I write a congruence like that. Okay? Yeah, so that's just one consequence of being of S approximating Z. All right, so now I think I'm ready to do the main proof. So these are all preliminaries. So now I'm going to prove. I want to prove that. So yeah, so I'm proving this this goal. Yeah. And so what do I? So I get to assume this condition A sub L. And let me for this talk, let me assume. Okay, let me assume that I actually have. Let's assume that my A is actually an elliptic curve, just to simplify it for this talk. I mean, the proof is not too different if it's not an elliptic curve. I'll still call it A, but so let's assume that there's an elliptic curve such that. Okay, so maybe I'll just write just so it doesn't look bad. I'll just say okay, can do with the Bjorn gravity cube. Okay, so all right, but let's okay. For today, let's just assume it's an elliptic curve. So it's an elliptic curve, and it satisfies and it has positive rank, so it has infinitely many rational points. And then has keeps the same rank over L. Okay, and so what do we want to show? Okay, so we're assuming this, and we want to show that OK is Diophantine, is over OL. So we need to write down a bunch of equations over OL. With a parameter, and then it's solvable when that parameter is an OK. All right. So yeah. So it's an elliptic curve. So yeah. So it looks like. Well, if you don't know what elliptic curve is, it looks something like this. Y squared equals. It's strictly speaking, it's the projective closure of this. It's the closure of this in projective space, but it's defined by some curve like that, where A and B are constants. Yeah, so with A and B are constants in the field K. So that's what we're talking about. And yeah, and then A of K are just the solutions to that equation where the X and Y belong to capital K. All right, so the assumption here is that A of K and A of L have the same rank, and they're finally generated abelian groups. So that means that one is that AK inside AL is a finite index because it's a subgroup of the same rank, and then because of that, if I multiply this group by the index, let's call the index R, and I multiply this by R, then that will be contained in here. And so, so for some R, so let's, so if I define this, so let me define R to be this time index. Okay. All right. So and now the point of doing that is that if I ask what kind of thing, which kind of things here are definable or Diophantine over OL? I mean, this is an equation. The solutions to this, but the solutions to this over L or over OL or over L. I mean, I talked about last time how you could represent L in terms of ratios of OL valued variables. So I can talk about the L solutions to this equation. So this set, I can think of this set as being Diophantine over OL. Okay, so that part's okay. Over OL. So so this is OL. I can think of this as being OL. Now I don't necessarily know that this one is OL Diophantine, although I guess actually kind of think of it. Oh, maybe I can. Okay, anyway. Actually, I guess it is. So because, I mean, this is going to be OL Diophantine. Yeah. Because I can write down what multiplication by R does. That's just some polynomial equations and so on. And now this is just a, yeah, I guess this, okay, actually, yeah. Okay, thank you all. So you simplified my proof. Okay, yeah, so this is just a finite union of cosets of this. So you can just take the finite union, each coset is going to be Diophantine, and now I take a finite union. So, okay, anyway, it doesn't really matter. All I really need is this infinite group that consists of things that are defined over K. So this is already good because I already have a set that's somehow defined over K. But that's OL Diophantine. I'm trying to get a particular one. I'm trying to get O sub K. Where's my goal? Oh yeah, it's right here. So yeah. So this is what I want to get. The O sub K is OL Diophantine. But at least I have this thing that's already something that's defined over K. All right. So yeah. So let's see. So yeah. Okay. So step one of this proof. Yeah, so this, I haven't even done step one yet. Okay, so step one is going to be that there exists an infinite OL Diophantine subset, set that's the set T, but that's contained in K. Okay, so and so the proof of this is just going to be, oh yeah, so I'll just let, well, it's quite easy because I have this infinite set of, I have this Diophantine set here. I'll just take all the x coordinates of these points on this elliptic curve, yeah? And there can only be 2 points with the same x coordinates. So I have a 2-to-1 map, and I look at the image of an infinite set. So the image is going to be infinite. So let this be x, the x coordinates of it. I mean, there might be some points where the x coordinate is, there's a point at infinity, but you can just ignore that one. So, okay, so that does that. Okay, unfortunately, not all the steps will be that easy. So I'm working my way towards defining OK. Here I got at least some infinite subset defined over K. So the next step is going to be to prove that there's an OL Diophantine set S contained in K that weakly approximates the integers. So this is saying that it's not just any old subset of K, but it's somehow quite a large subset. It's large enough that every integer is a limit of elements of that subset. So it weakly approximates these. Okay, so for the proof of this, all right, so I'm going to use the idea that's a little bit similar to what I used 2 days ago. I'm going to choose a uniformizer. So this is just in the sense of algebraic geometry at the identity, the point of infinity on the elliptic curve. If you want to be explicit about it, I could take. So z is going to be a rational function defined on the elliptic curve, and if you want to, you could just in terms of the x and y coordinates of the elliptic curve, which are themselves rational functions, you could take x over y, and this works because. If you know a little bit of algebraic geometry, you can check that if you look at the order of vanishing of the x and y at infinity, well, they have poles at infinity. That's why it's called infinity. X, y are both infinite there. But x has valuation -2, and y has valuation -3. So if you take this ratio, you get something of valuation 1 at infinity. And that's what uniformizer means. It's a function, rational function that vanishes to order 1. At that point. And so a uniformizer is also the same thing as a local coordinate. It gives you an analytic isomorphism near that point. So here's the point 0. And if you think of the z coordinate map, it maps that to the number 0. And so this is a copy of the affine line. Yeah, and so it gives you a sort of analytically, it gives you an isomorphism between a little open subset here, a little open subset here. Yeah, and in fact, it literally gives you an isomorphism over any field like the real numbers or p-adic numbers, anything that's any local field. You actually get an isomorphism between a little open neighborhood and a little analytic open neighborhood here and an open neighborhood here. So you can think of over the real numbers, well, the inverse, I guess, of z would give you like a little parameterization of points near there. And so that's how I want to think about that. Okay, so now let me tell you what S is. This set S is going to be. So I will take S. Okay, so S will be the set of ratios of coordinates of points. And so where P and Q are in A of K. Okay, so this is going to be a subset. First of all, it's a subset of K because, well, I by the way, when I write this, I ignore all the points where one of these is 0 or I mean, if this is undefined, you just don't worry about it. So, but if it's defined, then because everything is defined over K here. So these numbers is a ratio of elements of K. So this everything here is a subset of K. And moreover, this S is going to be OL Diophantine. And the reason that it's OL Diophantine is because we already proved that A of K was Diophantine. And then I'm just taking the image of Diophantine sets under maps and taking ratios. I mean, just the very definition of it just implies that you could write all this out in terms of equations. Okay, so that's just by definition. All right. Okay, so any questions? Now's a great time to ask questions. All right.
I have a question.
Yeah.
Maybe I don't remember very well my algebraic geometry, but isn't the fact that we are using elliptic curve in order to have a uniformizer, right? Or do we have uniformizers also for general abelian varieties?
For general abelian varieties, the notion of uniformizer gets replaced by the notion of a system of local coordinates. It's like how you think of it as like a manifold.
Yes.
And then in the elliptic curve case, it's a one-dimensional manifold.
Yes.
So you just need one coordinate. But on an abelian variety is like the higher dimensional analog of it. So, but at the origin, you can choose if it's a g-dimensional abelian variety, you can choose g rational functions.
Yes.
And then you can use those.
Yes. Thank you. And in this case, S would become like the set of ratios.
You take all the ratios of all the coordinates and
Yes.
take a big set. I just want it to be big enough.
Yes.
As long as it's, just make it as big as you have to. Just try to make something that's big enough, but it still should be in K, contained in K.
Yes.
So that's all right. Yeah.
Thank you.
I also have a quick question.
Yeah.
Were you originally going to use the smaller subset R times?
Yeah. I would just replace A of K by that RA of L. Not a big deal. But yeah. See, I'm sorry. You didn't really greatly simplify my argument. Yeah, but you did. Okay. Anyway, but it's nice to be able to write A of K. It looks cleaner. Okay. Good. All right. So but now the hard part is we need to prove that this set S weakly approximates Z. So I need to show that every integer is a limit of elements in S, and a limit p-adically for any prime p that I specify. So so let's take a particular target integer that we're trying to approximate, and try to find a sequence in S that approximates it. So one thing I can say is that if you take before I do this, let me just make this observation. If I take a prime and I look at this ratio, I take k. I'm going to take a point r on the elliptic curve, and I'll take k times the point using the group law of the elliptic curve, and then take the limit of this as the point r approaches 0. So I'm thinking of r sliding along the curve A up there, and tending towards the origin on the elliptic curve up on top, and it's doing this inside this sort of p-adic manifold, inside the kp points where I take the completion of k. So okay, and the claim. So what is this limit? Well, you can essentially use L'Hopital's rule to calculate this. So you can calculate the derivative of this as with respect to the parameter, and then the multiplication by k acts on the tangent space of the elliptic curve as multiplication by the number k. And so the derivative of this is like k times the derivative of this. So you find that this limit is k. Okay, I mean you can think of, yeah. Okay, anyway, that's going to be true. And this works for any r that's tending to 0 in this state of kp. But if you look back at the definition of weakly approximates, if you look at that second condition, it's not. It's not just good enough to have a single sequence of points that converges to 0 in one of these completions. I need to do it simultaneously in finally many given ones. So what I need now is a sequence of points in A of k that converges to 0 simultaneously in finally many of these completions. Okay, so for this, this is it turns out this is not too hard to do. So let me take a point here of infinite order. That's always possible because this is a finely generated group of positive rank. So I can find a point of infinite order. And then what I can say, if I take that A and I multiply it by n factorial, then as capital N goes to infinity, this will tend to 0 in A of kp. And that's just because, yeah, so this as n goes to infinity among integers. And this is because all this uses is that this group here, this topological group, is a profinite group. It's a projective limit of finite groups. And the way you usually realize it as a profinite group is you essentially look at the points on the elliptic curve modulo in O modulo p to the n. You look at the points mod p to the n, and then just as the ring of integers is just as zp is the inverse limit of z mod p squared, z mod p cubed, you can show that this, which is, well, okay, I mean strictly speaking you could use, okay, if you want to get technical, you could say you use narrow model and take the ring points over the evaluation ring, and then this is the inverse limit of this narrow model with values in O mod p to the n. Okay, but in any case, it's an inverse limit of finite groups. So that means if you have a point in here and you multiply it by n factorial, as capital N goes to infinity, all of the components will start being 0 one by one. Yes. And so eventually, so in the limit, it'll converge to the identity in this group. That's how the topology of this profinite group is defined. So this comes essentially for free from the fact that it's a profinite group. And so then you can now just plug that into here. You can use this subsequence of points that are, because now this holds not just for one p, it holds for all p. So now I can say, so thus, if you take the z coordinate of this, let's say k times n factorial. Let's see, maybe this is looking a little too confusing. let's say, I want to leave some space between the k and the n factorial a, because it's not supposed to be part of the, okay, factorial. Okay, anyway, so this ratio will converge to k in kp for every prime ideal p. And also, on the other hand, this ratio, visibly, it's an element of S. Okay, so that's exactly what I wanted. A sequence that converges to my integer simultaneously. Okay, so that's the trickiest part. So we're done with the trickiest part of the proof. Now I just sort of putting things together. Yeah. Okay. So once I have that, now the next step is to find a Diophantine set U that's it's big enough. It contains the integers, but it's contained in the ring of integers of the smaller ring of integers. Yeah, because I'm trying to get OK itself, but this is but this is getting me part way. All right, so how do you make this? So for this one, so to get this, I'm going to use the, I guess it's erased, but well, it's kind of here, lemma 1. So I don't know if you remember what that was. That was the one where you put some congruence and you put some divisibility of ideals to force an algebraic integer to be in a smaller ring of integers. And so here's going to be the definition. So I'm going to take all the elements in the big ring of integers such that there exists a number in S and another number in S such that if you take the ideal generated by this second one, then it satisfies this divisibility condition, alpha 1, alpha minus 1 to alpha minus n divides I. Yeah, sorry, this is a little bit technical, but anyway. And it's congruent to k. Mod I. Wait, that's not right. Mod I. Okay, so I'm trying to set it up to use that lemma 1. All right, so that's going to be the definition of a set, and I claim that this set is almost what I want. So I want to claim that this set. First of all, I want to claim that it's inside OK, and it almost contains all the integers. The only integers that's missing are the ones from 1 to n. So I'll have to fix that up later. But let's just do this for now. So yeah, so this first part, the first claim here, or this right hand, this inclusion, this is literally an application of lemma 1. Because I've set it, I've exactly set it up so that if there is this ideal, that's an OK ideal, because this little s is in this field K, and you have this divisibility and you have this congruence. This congruence, and so and the lemma 1 says that these are as long as n is big enough, I guess n is big enough. I get to choose n, so n is big enough. So then these conditions will force my alpha to be in the smaller ring of integers. Okay. All right, and now I now need to check that all the integers except for 1 through n lie in here. So let's do that. So let's check. Let's take an alpha in here and check that it's actually inside this set I just defined. So if this is true, then well, first of all, you can say, okay, so I'm trying to prove that alpha belongs to a set, so I need to come up with the k and the s and verify these conditions. So first, to get the s, I'll use the lemma 2. Is lemma 2 still? Yeah, that one. So I'll find an s such that if the numerator of S is divisible by alpha 1, alpha minus 1 through alpha minus 1. So I'll define the numerator of S. Yeah, so that's one of the conditions I want. I'm given the integer alpha, and I'm trying to find the S whose numerator is divisible by that. And that's what lemma 2 does. So, and then, okay, so next what I need to find the K. And the K has to be something that's congruent to alpha modulo this ideal. But that I can do too, by the fact that it's weakly approximating. So by the weak approximation, by the weak approximation property of S, there is going to be a K that satisfies the congruence, that's congruent to alpha mod I. And so, and then, so then just by definition, so now I have the conditions to satisfy all this, so that proves that alpha is in E prime. Okay, so that finishes the proof of the claim. So I have this set that's almost satisfying what I want. It's supposed to contain all the integers, but I'm missing a couple of them. Well, you can probably guess how I'm going to fix that. Finite sets are Diophantine. Unions of Diophantine sets are Diophantine. So let's try U equals U prime union 1 through n. Okay. Yeah. Oh, okay, so that finishes step 3. Yeah. Okay, so I'm not quite done because the goal was to prove that OK itself is Diophantine. Yes. Now I'm very close.
Yes.
I have a set that contains all the integers and it's contained in OK. So so let's see. Okay, so any more questions? Okay. Well, maybe I should leave up this thing I'm trying to prove. Okay, I don't know. Anyway, it's not going to be long now. I mean, maybe you can see already what's going to happen. Okay. Now I have to be very, very careful. Ooh. Well, anyway, so,
It is still readable.
Yeah.
What's still readable?
The thing you didn't want to erase is still readable, so.
I mean, it's almost all there, yeah? Okay, anyway. Okay, good. So, all right, so what's the last step? So how do I enlarge this U, set U, to make it all of OK? Yeah, so this is the final step, which is to prove that OK, this is the final goal, that OK is Diophantine. So, well, I mean, let me just choose a Z basis. So let's say B kappa. Let's say let's be a Z basis of OK. Yeah. And so now what I'll do is I'll take this set U, which I know contains all the integers, multiply it by each B sub I, and just take the sum of those sets, meaning that I take all possible sums of one element from each of these sets and add them up, yeah? So, I mean, it's pretty clear. Well, first of all, that's contained in OK, yeah? Because U is contained in OK, and everything here is in OK.
Yes.
On the other hand, I mean, among the possibilities for these coefficients I'm allowed to use are all possible integers. So this contains, U contains the set Z, so this is going to contain this. And then, okay, and then now you see what's happening. It's always nice when you end up with a bunch of inclusions and the thing on the left is the same as the thing on the right. So yeah, so the conclusion is that this equals okay, and but also the key thing here is that just by the way this is constructed, U was OL Diophantine, and if you multiply by BI, then it's still OL Diophantine, and then the sum of Diophantine sets is also OL Diophantine. So this proves that okay is OL Diophantine. Yeah. Okay. So yeah. So that's it. So thank you all for your attention.